All right. Thank you for the invitation to come here. And I've enjoyed my day talking with people about what you guys are doing here and looking forward to the chance to tell you a little bit about what my group has been working on over the last few years on these two-dimensional materials. And so today I kind of want to talk about how we can use these two-dimensional atomically thin materials to design new electronic and optical states, and how making structures where we stack the materials up can lead to new physics in these materials. And so, as Onar said, my group is really interested in studying local properties of materials through scanning probe microscopy. Primarily, that's done through scanning tunneling microscopy, but also we do it through some optical spectroscopy techniques as well. So things like looking at plasmons, so charge and light coupled oscillations in carbon nanotubes. Here's correlated states where we look at what happens when you couple superconductors with normal metals and image vortices and stuff in there. Some optical spectroscopy on materials. And what I'm going to tell you today about is these local properties of two-dimensional materials. And we're going to do that through scanning probe microscopy for about the first half of the talk, or maybe 2/3 of the talk. And at the end, I want to touch on some of our new results looking at these materials with optical techniques. All right, so what are these materials, these two-dimensional materials that we're interested in studying? So the first one that was sort of isolated, now I guess it's 20 years ago, in 2004, was graphene. So this is a single sheet of carbon atoms with this hexagonal lattice, honeycomb lattice, where you have a carbon atom at every site here, right? And then you can peel this down into a single monolayer sheet where you have just a single atom thick, and that was the first 2D material for graphene. So as I said, this was first sort of isolated in 2004 by Gaiman Novoselov. But if you go back and look, it was actually discovered in 1978 here. So this is sort of the first paper talking about monolayers of carbon. So carbon monolayer on a nickel surface. And so the material has actually been around now for 50 years, or almost 50 years. And if you look at the sort of impact of this paper, how many citations it has about 400 citations for that paper. And the question is, why did that paper not receive much attention, whereas the more recent discovery of graphene on insulating substrate from Gaiman Novoselov in 2004 here in this paper, if you look at that paper, has something like 30,000 citations, and this is now actually quite a few years old. It's probably 50,000 citations now. And so the real difference here is the ability to isolate these materials and remove them from their substrates and allow us to then study the intrinsic properties of the two-dimensional material. The first one I talked about, the carbon film grown on a nickel surface, basically the electronic properties are still dominated by the nickel surface that's lying underneath it. And so even though you have made this two-dimensional material, which you expect to have interesting physics in it, you are basically dominated by the more boring, if you like, material that's underneath the nickel substrate. What they were able to do here is to take this monolayer of material and put it on a boring substrate, in this case an silicon oxide substrate, which does not affect the electronic properties, and they could then access the interesting electronic properties of graphene. And in particular, what those interesting electronic properties that they were able to access is the dispersion relation, the energy versus momentum relation for the graphene. And that has this relationship where the energy is linearly proportional to the momentum, with this proportionality just h bar VF. And I want to contrast that with most typical semiconducting type materials, which have an energy versus momentum relation that has energy goes as k squared. So more like a free particle here with some effective mass in the denominator here. Graphene is more like photons, right? Energy is just directly related to momentum. K and P are momentum here. And in a photon, the relation is the speed of light, c. In graphene, that relation is the Fermi velocity. And so in this graphene, the charge carriers in the graphene, the electrons, quasiparticles here, are behaving like massless particles that are having a dispersion relation where they have a speed that's 1/300th of the speed of light. And so that gives rise to some interesting new physics in there because of this linear band structure as opposed to the quadratic band structure that is typical in most semiconducting materials. So graphene was the first one to be sort of isolated in 2004. 2010, Gaiman Novoselov won the Nobel Prize for the discovery and the work they did to sort of elucidate the properties of the graphene. But since then, over the last 20 years or so, there's now an entire periodic table, if you like, or an entire zoo of these two-dimensional materials. So what started as a single one in graphene has now gone to basically a material for any type of property that you're interested in. So graphene, I showed you, was this semiconductor or semi-metal. There are more traditional semiconductors like molybdenum disulfide here, which is then a 3-atom thick material with molybdenum sandwiched between 2 sulfur atoms. There's many sort of more traditional metals. There are superconducting materials like niobium diselenide and tantalum sulfide and some other materials. And then there are also insulating materials. In particular, there is a material here called hexagonal boron nitride. And so this looks just like the graphene structure, except that now instead of carbon atoms, we have boron and nitrogen atoms alternating as you go around this hexagon. And because these are inequivalent atoms, unlike the graphene where you have carbon, 2 equivalent atoms at the 2 different sites, you have very inequivalent atoms here, boron and nitrogen. And so there's a large band gap in this material. And it's a very good insulating material. There are also very many naturally occurring materials. Here's an example of mica, which you can find if you at least around down in Tucson. If you go around on the mountains and look around, you'll find lots of pieces of mica lying around, which is another one of these kind of two-dimensional materials, which is naturally occurring. And the key component is down here at the bottom. For all of these two-dimensional materials, you have very strong in-plane bonds. So the boron-nitrogen bonds here, the carbon bonds in plane are strong, and you have weak van der Waals bonds out of plane. And that's what allows us to take these sort of bulk crystals like mica or graphite and turn them into these two-dimensional materials. And so with this wide zoo of materials, then that has led to a wide range of electronic and optical devices using these materials. So the graphene I showed you before does not work very well as a transistor. It's not a good semiconductor, but if you take something like molybdenum sulfide, which is a good semiconductor, you can have a very nice transistor behavior. You measure the current here as a function of some gate voltage. You have 10 to the minus 13, and you turn it on here, 10 to the minus 5, so you get like a 10 to the 8 kind of change in the current through the device with a small gate voltage change. The other great thing about two-dimensional materials is because they are just a single atom thick, or maybe 3 atoms thick in the case of this material here, is that they make very good flexible materials. Unlike the sort of traditional silicon chips, which are in my laptop there or in my phone, right? Those you cannot bend. They'll just crack, they'll break. You can pattern these devices on flexible substrates, and they just behave exactly the same as they do in the sort of flat limit. Let me skip the photoluminescence here and talk a little bit about the multi-junction solar cells here. Because we have this wide range of different materials, we can tune their electronic properties by picking different materials. And here, if you pick ones with different band gaps, you can be sensitive to different wavelengths in the solar spectrum, and therefore get higher efficiency in a solar cell by just making devices with multiple materials involved. So how do we actually make these materials? So we're still making them the same way that they were made in 2004, and that is with a technique called mechanical exfoliation, which is just a fancy way of saying that we take Scotch tape and peel apart the materials. And so here's just a picture of one of these crystals on a piece of tape. You fold it in half, and because it's a van der Waals material, it likes to break apart into two different sides. And so you go from something that is maybe 1 millimeter thick to two pieces which are 0.5 millimeter thick. You repeat the process, getting half as thick each time. And once you've done the process like 40 times here, you have very thin pieces on the tape, and then you can press them on to a piece of silicon or a piece of plastic or whatever material substrate you would like to put them onto. And so after doing this, you have now transferred these bulk materials onto the substrate. And the last thing, the trick that you need to do is actually to go and find these, identify these materials on the substrate. And we are able to do that using basically thin film interference. And so these materials, even though they're only a single atom thick or 3 atoms thick in the case of molybdenum disulfide here, as the light passes through them, right, if they're on a substrate here, light comes down and reflects. Depending on the thickness, there's a little bit of a path length change for that reflected light, and therefore a slight change in the color or the absorption of the material, and that shows up then as a change in the optical measurement that we look at. So here's an example of a piece of graphene on a silicon oxide substrate, and you can very clearly see this is silicon oxide here. The kind of flower pattern is a monolayer of graphene. The next one in is 2 layers, and then 3 layers that get slightly darker inside. And so basically, just by looking at the contrast or the color, if this was not a black and white image, you can see how thick your material is. And the same thing will apply to these other materials. They come, though, in different colors because of their different optical properties. It's very hard to see, actually, here. The molybdenum sulfide is down here in the little triangle here. Boron nitride is a much wider gap material. It shows up as more of a green color, whereas the graphene shows up kind of more of as a purple color in the microscope. And so what we can do is we can identify the materials here. And then, as I said at the beginning, what we're interested in is combining these materials to create new designer electronic states. So if we have these 3 materials here as our building blocks, what we want to do is we want to take them then and combine them into a heterostructure where we vertically stack the materials in order to sort of engineer the electronic properties. And we kind of think of them as just Legos. They are essentially pieces of paper, if you like, also, and they can be stacked in any kind of arbitrary sequence that we like. This is in contrast to usual kind of crystal growth methods or something where you are constrained in how you can grow crystals on top of each other by matching the lattices of different layers. Here we have none of those constraints. They can basically put any lattice on any other one because we're not forming bonds between the layers. We're just stacking them with the van der Waals forces between them. And so the way we do that stacking is with a polymer stamping technique. And so what you can see here, this is a microscope objective. We look down here. We bring a little plastic, basically saran wrap on the end of a glass slide here. And we bring that down into contact with our sample. And we can peel off the 2-dimensional material that we're interested in looking at. And so kind of in a more close-up view of what this looks like, we have this polycarbonate plastic structure on here on a PDMS stamp, a little plastic here, squishy plastic. And we take this little bump, flip it over, and bring it into contact with our sample, like that. And so as we come into contact, we heat up the substrate. That expands the polymer here a little bit. It then becomes sticky. It then, as it cools, will pick up the material that's underneath it and bring it up onto the stamp. And so down, heats up, and we've picked up the material onto the stamp. And we can just repeat that process for whatever materials we're interested in putting on the stamp. And so in this case, we picked up something green here, probably boron nitride. Then we picked up tungsten selenide, and we continued to build some structure here. We build that entire structure, whatever we want on here, and then we can deposit it onto our final substrate by just heating the stamp to an even hotter temperature such that the plastic, this polycarbonate, melts. And when that melts completely, then it comes off the stamp here and ends up back on our substrate. And so here's just some examples of what this looks like when we've done it. We've taken, in this case, different structures here. So we have a blue one over here that's going to be something like tungsten selenide coming across here. We have pieces of graphite coming like this. You can't really see it in here, but there's another molybdenum selenide piece in here, and little graphite contacts to it, etc. Here you can see boron nitride piece on the outside, a graphene piece along here. Here's one with a couple different layers. And so as I said, we have basically any arbitrary combinations that we can make by doing this stamping. And so we're just basically going to choose our types of materials depending on the physics that we're interested in studying. And the way we're going to study these materials is with scanning tunneling microscopy. And so this is one of the scanning tunneling microscopes in my lab here. It operates at ultra-high vacuum so that we keep very clean surfaces. And so when we've made these samples, we need them to be basically completely clean on their surface so that we can come in with our little STM tip here and probe the behavior by bringing the tip very close to the surface. So we need this ultra-high vacuum to keep it clean, and we need low temperature to enable us to have good stability of the system. So by cooling down the system, everything basically is frozen, becomes solid, and that allows us to have our tip sample separation be very stable. The other thing it allows us to do is this sets the energy resolution of our experiment. So our spatial resolution is basically set by the tunneling distance. So that's on the order of angstrom. Spatial resolution. The energy resolution we get is set by kT. And so operating at 4.5 Kelvin, we get something like 1 millivolt energy resolution. And so I think everything I'm going to show you today is taken with this microscope. But recently, we've upgraded to a new microscope here in the lab. Here, we keep the same spatial resolution and same pressure in the system, but now we've lowered the temperature down to 40 millikelvin. So this basically gives us a factor of 100 improvement in our energy resolution. We go from basically 1 millivolt down to like 10 micro EV in there. And so we just got this system up and running a couple months ago now. And so hopefully we're going to get some very interesting new results by being able to probe even lower energies in these systems. So the types of measurements I'm going to show you today are primarily going to be topographic measurements and spectroscopic measurements. So in the topographic mode of the STM, we have our sample here. We bring our tip up to it here, and we measure the tunnel current that flows between the tip and the sample. That tunnel current depends on two things. It depends exponentially on the distance between the tip and the sample. So it falls off as 1 over the distance there. And it depends on this integral of the local density of states. So basically, how many states are available for the electrons to tunnel into in the material over whatever energy range we're integrating over. In the topographic mode, we do this with a constant current. So we use a feedback circuit to keep the current constant. If this density of states isn't changing too much, then the current constant basically means that Z is being constant here. So we're basically mapping out the topography of the sample. And so that's what you see here on the left-hand side of a picture of a graphene sample. The color scale is basically the height of the sample as we scan across it. The other mode we can operate in is, instead of this topographic mode where we're scanning with a constant current, we can go to a fixed location. We turn off that feedback circuit, but we keep the tip height fixed. We keep Z fixed, and we change the voltage. So we change the V here. And so that's going to change how many states we're integrating over. And so if we then look at how does that current change as we change this voltage here, Well, that's the derivative of this. That's giving us basically this local density of states information. So that's giving us the number of states which are available for tunneling at that current position as a function of energy. And so that's what is shown here. I'm going to show you a lot of these type of images here. So this is density of states as a function of energy here. So there's very few states here, and you can see it increases as we go either direction from here. And so this is the characteristic spectrum that you get for graphene. I showed you earlier, right? The energy versus momentum relation was this V-shaped cone. In the density of states, what that shows up as is these kind of linearly increasing bands on either side. And the real power of the STM then comes from actually being able to combine these two measurement techniques together, topographic mode here, and taking local density of states at all of those same locations. And we can combine those and look at how they are the same or how they vary from each other. So if I go zoom in here, this is the topographic map here, and I have these hexagons that are characteristic of our graphene lattice. But if I go in and do the same thing here, I have some pattern down here in this local density of states as well. And you probably need very keen eyes to notice, though, that they are different from each other. So this topographic, showing us where the atoms are, is varying from here where the density of states, where I can tunnel into the system. Right? So there's not a one-to-one correspondence here. And the difference here is due to some electronic band structure things in the graphene. And so that's going to give us information about the allowed scattering and the different electronic properties. And that's what we're going to use to probe these materials. All right, so I've spent 25 minutes or so here kind of motivating and talking a little bit about what we're interested in studying. And I want to, in the second half here, kind of tell you three different stories. There might actually only be two different stories in the end about what happens when you combine these materials. And in particular, what we're interested in is what happens as you take two different materials and you apply twist angle to them. You change their relative orientation of their lattices. So first, I want to tell you a story of what happens when you do that with graphene. So graphene on graphene, two monolayers of graphene, and you play with the twist angle. Then I'll talk about what happens when you do it with two different semiconducting transition metal dichalcogenides. And I want to tell you a little bit about why those two are different from each other. And then if I get a chance here at the end, what happens when you take not two of the same materials, but two different materials together, and show you some results here where we have a superfluid can form in this heterostructure. All right. So in this graphene on graphene, if you want to make this heterostructure where you control the twist angle, it's very important that you are able to very well define the twist angles between them and accurately control them, because the electronic properties are actually going to be quite sensitive to that twist angle. And so we developed a technique to actually do this with a very controlled rotational alignment between the two layers. And so what you see here, this is a monolayer of graphene up here, and we tear it in half. So we cut it in half at this point here where the white dashed line is. That way we know that the two pieces of the graphene are exactly the same crystal alignment with each other. We pick up this first one onto the stamp, and then we move the stamp, just a translational motion, over to here, and then we pick up the second one after some known rotation of the stage. So basically you tear one half up, move over, rotate some amount, whatever rotation angle you want, and you pick up the second one, and therefore you have the two pieces on top of each other. And so what that looks like here is that you have these two layers, and as you twist them, you can see their properties are going to change in terms of what the stacking looks like. So as I rotate these around, you see there's this moire pattern that forms, went out and back in. Here, it's going to go out again here in a second, as this comes out and goes in. And so there's a new periodic structure that's formed in this heterostructure that's not present in the individual layers. Right? The individual layers have an atomic sort of structure of a few angstroms for their periodicity. here, by tuning this, we can change the periodicity of this structure as a function of twist angle, everything from the very small, when they're 30 degrees out of rotation, to when you go right near 0, you can get extremely long periodicity structures. And so this is obviously just a PowerPoint animation. If I go and show you what it actually looks like in the STM, here's 3 different images of what this moire pattern, this twisting, looks like in graphene sheets on top of each other. It's not too hard math to figure out what this wavelength should be as a function of twist angle. It basically boils down to going as 1 over the sine of the angle between them. Here, you can see the size scales, 3 nanometers, 30 nanometers, 50 nanometers. So we're changing the twist angle. We're getting smaller twist angle as I go to the right here. And at first, you can kind of maybe see the little graphene hexagons in here, the little tiny hexagons. And then there's this periodicity that is on the order of 5 nanometers in this guy. The periodicity now, you can no longer even see the atomic lattice, but we have about a 30 nanometer periodicity here. Still looks relatively the same as this, little white dots and uniform areas around it. You go all the way to 50 nanometers, and it starts to actually look very different. We still have these bright spots, but now there's these like lines that are connecting them here. And so there's going to be changes in the electronic structure in this material here as we go to the very small twist angles. And so let me just try to, in 1 slide or 2 slides, talk about what the electronic structure we expect in these materials are. So graphene by itself, this monolayer graphene, I already told you it should just be this energy versus momentum relationship, which is just a cone. If you have no twist angle here, well, let me call this AA stacking, so the atoms in one layer are directly above the atoms in the other layer, then it's basically going to be 2 copies of that same band structure on top of each other here. And so you just have that same linear dispersion. If you stack the graphene in this AB or Bernal stacked configuration, you have basically the yellow atom here is directly above a red atom here. In that case, the dispersion relation becomes quadratic. Energy versus momentum relation becomes quadratic here. If you stack it in the opposite configuration, the BA, so red over yellow instead of yellow over red, right? That's going to be exactly equivalent. It's just flipped over. It's like looking at it from the other direction. So you should have the exact same energy versus momentum relation. Now, if I apply an electric field in the z direction perpendicular to here, that's going to break this inversion symmetry in these 2 structures here, and that's going to then open a band gap in the material. So these little dashed red lines are showing what happens when I apply an electric field. Here, it does not do anything to it, and we just keep the same structure. And so basically, if I have a configuration here, I have one that stays a metal, and I have another set of stackings which become semiconducting or insulating if I'm near the center here. And so I get changes in the electronic properties with the electric field depending on the stacking configuration. And now let me show what that means in terms of in a space. If I have a uniformly stacked Bernal graphene, AB everywhere, and I have an electric field which I vary direction from into the plane to out of the plane as I go across the space here, well, that's basically changing the field like this. At some point, the field is 0. And we have gapped regions on either side, 0 field in the middle. So it's conducting in the middle, gapped on either side. That is going to be exactly equivalent to changing the stacking configuration from AB, smoothly changing to BA, sliding the graphene on top of each other, but keeping a uniform electric field. So these 2 are equivalent to each other. And what that means is that along the domain boundary here, or along the 0 of the electric field, there should be conducting states which are going to be topologically protected in this system. So they're protected here and here. So we have the gap states, and then we have 2 topologically protected states which live along the edges of these graphene structures. And thankfully for us, this twisted bilayer graphene gives us that exact geometry that we need to observe these topological states. This is zoomed into the one I showed you earlier. These bright spots are where we have AA stacking. And then we have AB and BA stacking alternating going around them. And there is some kind of domain wall separating the different stacking configurations. So what we're interested in is probing the electronic properties of this structure at the different symmetry sites here. So this AA site, this domain wall, this AB sites, etc. And so that's what's shown here. So the color scale is the density of states. Bright means high density of states. Dark means zero density of states, or in the middle of a gap. And what I'm doing is I'm probing as a function of energy in the y-axis, and the x-axis is the electric field that I'm applying to the sample. So let me maybe start with this AB stacked region. If I have zero electric field, I have basically fairly uniform density of states. As I apply a larger and larger field here, I get this region of black showing up here. That means I'm opening up a band gap in a sample. There's a region where we have no states available for tunneling. That's the band gap in the material. And so that's where it's gapped. In the AA site, okay, there's kind of a bunch of crazy lines going different ways here. I think for this talk, I'm going to just kind of ignore what's happening on the AA site. There's actually lots of interesting physics there, including superconductivity and other things, but we're going to have to skip that today. And then on the domain walls, we just basically have things which move fairly uniformly with the electric field. Nothing really happens with electric field. So if I go and now look spatially at this, if I look at an energy above the band gap, so at a high energy, I have pretty much uniform density of states. So again, color scale is density of states. White or orange is high. Black is low. These dots here are these AA sites, which I said we're going to ignore. But other than them, it's pretty much a uniform density of states. The electrons are happy to go wherever you want. As soon as you lower the energy, the AB and the BA sites, these triangles, their density of states goes down because you're within the band gap of them. But no matter how low you take that energy, there continues to be these two bright lines along the domain walls. And so these are topologically protected states. So the electrons live along these domain walls and still can transmit through the sample. So if you were to do an electrical measurement here, this thing would still be conducting, even though you have all of these regions of insulating states in the center. So that's what happens in graphene as you adjust the twist angle. This only occurs at very small twist angles. Before that, you don't, at larger twist angles, you don't create these well-defined different domain structures to allow this topological states to form. All right, so now let me move on and talk about what happens when you take two TMD materials and you do the same kind of twisting on them. All right, so as I said, there's this range of materials beyond graphene. I'm going to focus just on these 2D chalcogenides for this talk here. And their structure is a little bit different than graphene. It's still, if we look at it from a top view, looks the same. Right? It's still got this honeycomb or hexagonal type structure. And in the monolayer, we have our metal atom here, tungsten, and the two selenium atoms like this. But now there are two different ways to stack these materials on top of each other. We can stack them in this kind of AB configuration, where the top and bottom are rotated 180 degrees from each other, or we can stack more in this AA configuration, where they're pointing still the same direction. In graphene, because from a side view, the graphene is just a single carbon atom, there is no difference in graphene when you stack them here in what the sort of side view would look like. And so this actually is going to have an important effect on what the electronic states will look like in these TMD materials. So In case you're not familiar with them, they are semiconductors with band gaps on the order of 1 to 2 electron volts. And so if we go and we look at them here in monolayer and bilayer, we basically can measure the density of states as a function of voltage here to probe the band gaps of these materials. In the monolayer, the white here, we have a gap of, I think it was 2.2 eV for the monolayer. And you create a bilayer. These bands slightly shift here, and the gap reduces to about 2.1 eV. But there's not actually a significant change in the band gap as you add a second layer to it. But there is a significant difference in what the wave functions are going to look like. And so let me look now at AA-type stacking. So that means a 3-degree twist angle between the layers. And this 180-degree rotation version of it, which I call the AB type, where we've rotated 183 here. And so on here, they kind of probably look identical to you. And they are, except for the microscopic stackings here. In this case, we have states which have like AA-type stacking directly on top of each other. Here we have ones which are the AB-type stacking. And then if you start looking at how does the chalcogen and the metal atom stack on top of each other, here there's ones where you have metal on chalcogen, chalcogen on metal. And in this one, you don't ever get that stacking. You get either metal on metal or chalcogen on chalcogen. And so there's actually 6 different sort of high symmetry type stacking configurations that you can have. 3 appear in this top case, 3 appear in this bottom case. And because of that, if you go and look at what happens to the band structure in these materials, you end up getting slightly differences between them. But in both cases, as you make the twist angle small, you get large domains here. And the valence band that had this curvature to it flattens out. And you end up getting a very flat valence band in both cases. And the sort of bandwidth or the thickness, how much curvature there is in that band, drops down with twist angle. In both cases, going towards 0, becoming a flat band as you approach either 0 degrees or 60 degrees. And so that's the bands that we're interested in studying, is what happens when you make these bands flat so that they have very little dispersion in them. Because at those points, you expect to have a very high density of states. And that's where you'd also then expect to see correlated electron phenomenon. So we made 2 samples here, one of the 3-degree type and one of the 183-degree type. And then we wanted to go and probe them from first a topographic point of view. So if you look at topography here, the color scale is the height of the sample. White is high, dark is low. And you'll see these look fairly similar. There's a series of white spots in both cases. Orientation may be slightly different from each other, but they have a periodicity which is identical. So this 6 nanometer scale bar is about the periodicity here and here as well. So it doesn't matter the twist angle that you have the same periodicity between them. And from this images here, we can go and we can actually identify what are the stacking configurations. How do the different atoms sit on top of each other here? By going and taking high resolution images here, we can determine what each of these stacking configurations corresponded to. And once we've done that, then we can go and look at the electronic states of these different ones. And let me just look at this 3-degree twist angle one. And so unlike graphene, which had a pretty simple band structure with just this like single X, here this band structure is actually fairly complicated. There's lots of different maxima occurring at different states, different momenta here. And so there's a couple different bands in the conduction band here, another one slightly offset, a third one here. And so the band structure is complicated, and that means that when we do this measurement of the density of states as a function of energy, there's lots of little shoulders and bumps in here. And those each correspond to as we change the energy and hit each one of these different levels. So when we hit QC here, that state turns on. As we go a little higher, we hit the Kc, that point up there, and similar things over here in the valence band, the gamma point here, et cetera. And so this actually took quite a bit of modeling to work out what these points correspond to, because what I gave you before for the simple picture of this density of states, e to the minus some value times z, is slightly more complicated because this decay constant here depends on the momentum that you're trying to probe here. And so it's easier to probe states which have zero momentum here on the left-hand side. Probing states which are out at finite momentum, they decay more rapidly and are more difficult for us to probe. So now let me take, instead of just a single point here where we look at the density of states at a single point, let's go and map the density of states as a function of position across the sample. And so I'm only going to show you the valence band because that's where the interesting physics is occurring. So the color scale is the density of states. Dark color, blue and black, are zero density of states. White is the high density of states. This is the band gap up here. This is the band edge here. And you can see there's these states that show up near the band edge at different positions along the sample in space. So there's some here, here, nothing happening really at the AA site, et cetera. So that's a one-dimensional cut through there. If I take a two-dimensional image of it, this is what this state looks like. So I'm taking this image just at this particular energy here. And what I see is that the electrons are all living on the edge of these hexagons. Right? So they're living along certain stacking configurations in the sample. These are calculations of what the expected density of states looks like in this structure, which matches fairly well here if you look at the unit cell of how the electrons are sitting. Do the exact same measurement with the 183-degree twist angle. Same physics is happening. You have this twist angle, you get these flat bands, you get states living along the unit cells here right near the edge of the valence band. But if you look back here, right, this is on the edges of these hexagons up here. If we compare that to here, these are now in the center of the hexagons, right? The hexagons have low density of states. There's actually a slightly brighter on one site than the other on the inside of the hexagon. And that also agrees fairly well with the theory calculations. And the difference here between these two is all coming from the fact that you have this 3-atom structure in the tungsten selenide, and there's a difference between the stacking of 0 degrees and 180 degrees. And so that's leading to then different confinement of the electrons and different wave functions than in the material. So that's what happens when you take homobilayer, two of the same materials, and stack them on top of each other. You can also do the same thing with a heterobilayer. So in this case, instead of 2 layers of tungsten selenide, we replace the top layer with molybdenum selenide. And so the same kind of stacking configuration, 0 and 180 degrees, turn out to work here. And you get roughly the same type of stacking configurations. And now if we go and look at the band modulation in this material, so we're looking here at the valence band, the conduction band up here and the valence band down here. What you'll notice is that there's actually a fairly strong modulation in the band gap as a function of position in this material. And so basically, the band gap is the difference between the yellow line here and the yellow line here. So it's small band gap here, larger as we go here, it gets smaller, larger. And so there's this modulation that occurs. And so what that means is as we put electrons into this system, right, they're going to want to localize here for our holes at this point, and our electrons are going to localize at the bottom of the conduction band. And so where the electrons and the holes are sitting in this are going to be at different positions at the different points there. And so that has important properties for some of the optical effects in these materials where you're creating excitons or combined electrons and holes here and how they behave in there. And a similar thing will happen in the R-type materials here. I'm only showing the valence band because the conduction band doesn't have any modulation. So all of the band gap modulation occurs in the valence band. And you can see it's on the order of like 200 millielectron volts, 0.2 eV. So this is actually a very strong effect in this modulation of the band edges in these materials when you go to the heterobilayer and mix different materials together. All right, just a couple more minutes maybe here to talk about a little bit more about the optics then of when you put these materials together. So as I alluded to on the last slide, if you have this combination of molybdenum selenide, tungsten selenide, you can create an electron in one layer and a hole in the other layer. And so the electrons are living in the conduction band of molybdenum selenide. The holes are living in the valence band of the tungsten selenide. And so that will then allow you to create a long-lived exciton. So basically a bound state of these electrons and holes. Because they're living in different materials, they can live for a long time. If you want to make them live even longer, you want to bring these materials apart, make it harder and harder for those excitons to recombine. So in this case, I have the materials in contact. The electrons and holes are here. As I bring them apart using a boron nitride spacer, I separate the electrons and holes. I make it more difficult for them to recombine. And I then increase the lifetime of this state. And the reason I want to increase the lifetime of this state is I want to make a lot of these particles here. Because if I can make a lot of them, I can make them into a condensed state and into a superfluid. And so basically what I'm trying to do is to create a superfluid of these excitons, these charged neutral particles, by making them extremely long-lived. And so I only have maybe a couple minutes to go into this, so I'll probably have to skip most of the details, but I hopefully can just show you quickly the results here. So I have this device where I have on the left-hand side them well coupled, the two layers. On the right-hand side, very decoupled from each other. And I want to see if I can basically create a superfluid state, or in other words, can I create coherence so that everything has uniform phase in this entire region of the sample, and over here it's just random phases. And so that's what I'm trying to depict here. I want to have uniform phase here. I have a macroscopic state in this side of the sample. And so the way I'm going to do that is I'm going to actually image the emission of the PL, the photoluminescence from this sample, and I'm going to interfere it with itself. So I'm basically going to bring the emission in here, split it into two arms, and recombine it together. And I'm going to take the two images and rotate them 180 degrees. So I'm going to interfere this position of the sample with this position of the sample. If they are a uniform macroscopic state here, then I should be able to interfere those two positions. If there's no correlation, then it'll just be like two separate photons, and I'll get nothing interesting in the interference. And so unfortunately, the colors are very muted here. Hopefully, something will show through here. But this is basically a little red dot here. That's the photoluminescence coming from this side of the sample in one arm. In the second arm, I take this sample, I rotate 180 degrees. Now you see the emission is down here. So these two are like this. And then I take them and I put them on top of each other. So I combine the two arms together and I see these interference fringes, right? So that is my evidence that these guys are constructively or destructively interfering. There is coherence between them. I'm taking points in the sample that are over here with points that are over here, combining them, and I'm getting an interference between them. And to really show that, what I can do is I can take this mirror and I can change the path length here. I'm basically delaying the time it takes on one path compared to the other. I'm changing the phase that the electrons accumulate there. So as I time delay this, these fringes will move. So if I look at this point here, it oscillates in time just because the path length is changing. And so by looking at how they oscillate, how strong they are, I can make a map of how coherent the sample is as a function of position. So this is showing basically there's coherence everywhere. I have this blue region. There is coherence. Out where there's black, there's no coherence. I do that as a function of the density of these particles. I control the density by how much power I put in, by how much laser power I use for excitation. At low laser power, there's only coherence right at the center. That's basically the same point overlapping with itself. So of course, it's going to be kind of self-coherent. As I increase the power, that coherence grows and gets eventually over the entire area of the sample. The last check I can do with this is what happens as I change the temperature of the system. So as I warm the temperature up, I expect that this superfluid state would melt. And that's exactly what I see here. As I go from 1.6 Kelvin, as I increase to 15 Kelvin, I had fringes everywhere here. And now the fringes become more localized here. And there's this kind of transition here with temperature and density, which agrees quite well with the expected transition temperature there. And so let me just, I'm going to skip the last couple slides there and just say that we can do this kind of things on a wide range of other materials. So I picked basically 3 to tell you about today. But in terms of, we can couple graphene to a semiconductor and look at interesting things. Graphene on topological insulators, we can basically create a topological state in graphene, couple it to a superconductor. There's a wide variety of, almost an endless variety of different combinations that you can have. And so hopefully today what I've shown you is that by choosing different materials and the different ordering and controlling their rotation and their separation between them, we can induce new physics and sort of correlated states in these materials. But as I end here, let me just actually acknowledge the people who do the work, because I don't do basically anything. I am too busy doing other things to spend time in the lab. So this work is done by a bunch of students in my group. The ones in red are former students, and my current students, Mohammed Aldiyar and Anna, are the ones doing the current measurements. And also we have a strong collaboration with John Shibely's group, also at U of A, and his students who do a lot of the optics type measurements, some theory and sample support from other people and funding agencies. And thank you for your attention.